Another concept I need to explain is why do we even need encoding? Why do we have these terms encoding or decoding in this program anyway? I mean, we are handling just those tiny tracker files, right? I mean, it's not MP3 or WAV data. So why do we need to compress data? Well, actually, we have all these. Well, the conventional method to save a tracker file would be to save every cell that you can see here, but all those cells are empty cells. They still have to be saved though, right? I mean, one cell contains 1 byte, is a 1 byte information. So you can imagine if we have to save all these cells, even the empty ones, we have a data the size of around 2 kilobytes. So when you have a pattern containing 30 different patterns, that would already be in data as large as 53 kilobytes. And that's unbearable. So the first idea I had for compressing those files, the data, was couldn't we save anything but the empty cells? So that was my first idea. So we just save the information where our command data is and in which row and which value it has. Let's say you want a C here, it's in the 7th position and it's a C, for example. But that would be a 2-byte data. That actually means when we fill out all these cells that you can see here, we would even exceed the amount of memory we would waste actually. And that about the size a double. So instead of just wasting 53 kilobytes, we would even waste 107 kilobytes. So that's also not something we could do. So my second idea was, couldn't we combine the best of both worlds and leave out the bad parts? And that's what we're doing here. Wait for a moment. We say to the program, to the encoder and the decoder, there is a command after the 4th position. You have 4 rows, then your first command appears and then another command appears, and this, I call this time vectors. After 4 rows a command appears, that's a time vector. And when we have the time vector 0, there is no time vector stored then. So, and otherwise 2-byte information is just a 1-byte information this way. So we're reducing the memory space to 1 byte. So when we fill out every cell that you can see here, every cell, we would still exceed the amount of memory of the conventional method, but not the double amount, just somewhat 100 bytes. I will explain that later why. But it's not the usual composing behavior to do that, right? I mean, see, this is a normal song. This is what a song normally looks like, usually looks like, and you don't fill out every cell. You could do that, but that's not normal composing behavior. So so when we compose a normal song, we on the average we just need 10% memory space of the conventional method. So instead of 53 kilobyte or 107 kilobyte, we just only need around 6 kilobytes or 5 kilobytes. Yeah, so but how are we doing that? How will we do that? Well, this here is the actual code, how it looks like. First of all, let us focus on this example right here on the right. So let me explain the codes. This is how the algorithm decodes and encodes the sound commands. So we have column 3, 0, 1, 2, 3, 4 rows, 1, 2, 3, 4. And then the first command appears, then 2 rows, 1, 2, and another command appears. Then we have in the column 5, 0, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6 rows. The first command appears, another row, another command appears. So after that we have the separator number 126. It separates the time vectors that you can see here from the actual command values which are stored after the separator 126. It is actually an C, another C, a 2 and another 2 respectively in their ASCII values. As you can see here, 67, 67 which is a C, and 50 and 50 which are 2s that you can see here. So this is how the codes of one pattern looks like. But now let's discuss this exception right here. So we have an A, and after that A another A appears, and there is no space between them. The time vector here is 0. So how does the code look like now? So first of all we're going to the column 3, which is 1, 2, which is 0, 1, 2, 3, 6 rows, 1, 2, 3, 4, 5, 6, and after 6 rows the first command appears. So but now another command appears, but it's not stored here as information as we had it here, right? We have 4 rows and 2 rows for the second command, but here's the second command right after the first command, so it's just the A is stored here. This is that second A. This is the information for the first A, where the first A is stored, and this is the second A. Then we have the separator, and after the separator the A appears, and it's just the value of this first guy here from from this guy here, and this is how the code looks like. 93, which is the column, we're starting at 90, 90 is 0, I will explain that later why, and after the 6th row the first command appears. So then you might ask, what is this good for here? We have the number 84 and it represents the same value as 65. You might ask why. Well, that is because the first 64 numbers are reserved for the time vectors. So you have a number like 6, for example, or it could be 12 or 5 or 2, and it goes up to 64 or 63. So we can't store the values from 2, for example. 2 has the ASCII value 50. That wouldn't fit here. The program would recognize it as time vector and not as actual ASCII, as actual command value. So we have to add another number, the number 17. Number 17, and we can store every ASCII value we actually have. So we're starting at number 0, which is the ASCII value of A48. That would be an ASCII that would be converted to 65 here, right? We're adding to the number 48 the 17, and we're getting the number 65. That is our 0, and 84 therefore is the value of A. So you add to the number 65 what would be the actual ASCII value of the letter A. We're adding the number 17, so we're getting the number 84, and that's stored this way. You should rewatch this part of the video several times to don't forget it. Don't forget, it's very important. It's very important. You should remind yourself if you want to program this on your own and want to do it the way I did it. So yeah, okay. What else do we have? So you might ask, why do columns start at number 19? Well, as I've already said, the first 64 numbers are reserved for the time vectors. So another from 65 to 89, these numbers are reserved for command values, right? You have the 65 as 0, represents our 0 before the separator 126. After that it's just a normal ASCII value, reminder. And well, yes, so we're starting from number 90 to describe the columns. So column 90 is actually from the first channel, it's the 0th position, 0th column, and we have 28. We're going through 28 columns. So yeah, that's how the columns are stored. The value 126 is, as I've already said, a separator. It separates the time vectors from the command values. And we have another separator, it's the number 127. 127 shows the algorithm or the program that this pattern is finished. This is all the information that you can see here. This is an entire pattern. This is like this, but it just stored this piece of information, nothing more, and that's how this would look like in code form. This is our actual commands that are stored here, and this is one pattern. So we have another separator, the separator -128. I will explain that in a minute. I forgot to unsign my variable, so I have to handle minus numbers as well, negative numbers as well. But this isn't a huge issue because I handle this information, this data, as binary anyway, so it's not a problem at all. So how does the code actually look like? This is a tiny example of this code. We have a song here. In the first pattern we have just one command and the other patterns are all empty. So how would the code look like actually? Well, we have column 90, right? We have 1, 2, 3, 4, 5 rows and the first command appears. We have the column 93, which is 0, 1, 2. Well, actually this would be the number 92. Sorry for that. And in the 5th position, after 5 rows, we have another command. So then the separator number 126 appears, and we have the actual command values 67, which represents a C in ASCII, and 53, which represents the number 5 in ASCII code. After that we have the number 127, which marks the end of this pattern, the pattern 0 that you can see here. So what else is stored here? I've already said in pattern 1, 2, 3, 4 is no information stored. They are completely empty. So how does the code look like after the first pattern? We have 126, 127 ends. This is the end of the first pattern, 126, 127, the second pattern, and so on and so forth. There's no information stored, but the separators are there for the algorithm to recognize where we actually are in our piece or in our file. So the separator -128 ends the song. It marks the end of the complete song. While this just ends the end of the pattern, marks the end of the pattern, this marks the end of the entire song. So so this piece of this file here would actually, if you would save every empty command cell, this song would be already 8 kilobyte large, and that's pretty bad, right? I mean, we don't have any information stored here. We have just this keynote here, and that's the entire song, right? And the other patterns, there is not even any information, but it's an 8 kilobyte large song. That's but this way, if we save it that way, it's just 17 bytes. If you leave out that part, I will explain that later. From here to here, we're just storing 17 bytes, and that's pretty decent for a song of this amount, a so-called song. That's okay, right? I mean, that's okay. So what is stored after the end of the song, minus 126, that separator, we have the pattern nominators. They're actually very important. They tell the program which pattern is actually to play and in which order. We've arranged in 1, 2, 0, 1, 2, 3, 4, but we could rearrange them in any ways, right? In any order. We can say pattern 22 is here, and 25 is here, and 6 is here, and 1 is here, and yeah. So after that we have the separator number minus 127. After that we have the wavetable preset. So I've already shown you that we can make triangle waves and other wave shapes in the wave editor, and that preset is actually saved here in this 8 bytes information block. These are 32 2-bit sample data. So as you have seen in the wave editor, you can choose between 0, 1, 2 and 3, which is a 2-bit data set, and we save that piece of information in these 8 bytes. And that's it. That's the entire code of this example here, of this so-called piece of music. And C note played in the first pattern, and all the other patterns are empty, and that is how it looks like. So yes. Okay, how else can we save memory space? Well, it's pretty self-explanatory. When we have patterns several times the same pattern, we have copies of the same pattern, they're just links to this pattern right here. So we're just saving that in our file one time, not 2 times or several times, right? That's a way to save memory as well. Yeah, and this is the other core concept I want to explain. That's it, right?